contraction of the ventricles, blood is pumped out of the heart. Stroke volume is the amount of blood a ventricle pumps out in one contraction. Cardiac output is the volume of blood that each ventricle ejects every minute. To find the cardiac output volume, multiply the number of heartbeats in 1 minute by the stroke volume. At rest, the cardiac output for an average adult male is about 5.25 liters, 4.9 liters for an adult woman. Cardiac output increases with physical activity, rising to a maximum that may be 4 to 7 times greater than the resting output. This difference between resting and maximum output is known as cardiac reserve. Heart rate and stroke volume are regulated by the autonomic nervous system and by hormones in the bloodstream. Other factors such as age, weight, and physical fitness also influence cardiac output.
Alright, that's just a trailer, things to come, right? Stroke volume, cardiac output, did y'all talk about that? No, we will, don't worry. Okay, so things about the cardiac muscle, found only in the heart, obviously that's why it's cardiac, okay? It's involuntary, we don't have control over our heart, we can't say, oh, hey, stop, rest for a minute, right? Or we would want to, nor would we want to. Has its own blood supply, the coronary arteries. So when we talk about the coronary artery system, we won't go into memorizing the coronary arteries, just a couple of them, the big ones, right? And then it contracts on its own. It has excitability and contractility, meaning that it can contract, the cells can contract, and then automaticity. These three here are the property of each cardiac cell. And in the heart we have different cells, right? We have conducting cells. Let me see if I can remember them off the top of my head. Conducting cells, okay? We have contracting cells. And there's one more. Conducting, contracting. I'll come up with it later. Alright? Anyhow, we have these different types of cell, but the properties of a cardiac cell are these. These are the three properties of the cardiac cell. It begins with excitability, meaning that the cardiac cell is able to create an action potential. Now, I know this is going to sound like really vague here and there, and we'll put all this together as we go through in many weeks, okay? But just hang on, I'm just sort of introducing some terms to you right now, okay? So the three properties of the cardiac cell, one of them is excitability. Excitability is the ability of the cell to create an action potential. External from the brain, right? This is what the cardiac cell can do. It doesn't require a response like a skeletal muscle from the brain. So it can create an action potential. It's automatic. We don't really work with that, okay? That's automaticity, means that it happens automatically. Once a cardiac cell starts contracting, it will contract until it dies. That contracting cell. And then contractility, so the cell will contract. We can live without the brain. The heart can beat away perfectly without the brain, correct? Is that true? Yeah, a patient can be completely brain dead. I mean, like zero from the EEG, and the heart working perfectly. Because it doesn't require the outside stimulus from the brain, really, okay? So these are the things that it will do, and as we develop this throughout time, we'll work on this, okay? We'll skip this one for now. That's a bit much, okay? So cardiac conductive system, the three properties of it: excitability, conductivity. Remember, it will conduct, has automaticity. It does it without outside response, and then it's able to contract without an outside response. Me holding this remote, the brain is telling my muscles to contract and hold it, okay? The heart doesn't require that. It doesn't require an outside stimulus. That's important. These are important to understand about the conductive system of the heart. Just a quick picture. Later, sometime 5-6 weeks later, we'll go into this cell quite extensively, okay, where we have these different parts. I just want to sort of throw it up there and introduce it to you right now. What takes place, like these gap junctions here, that's responsible for the conduction of the electricity. Let me see if I get these discs. I think it's the dermazones, something I'm going to have to review as well, right? Keeps that muscle, that heart muscle, from being pulled apart when it contracts, because it contracts with force, right? And of course the mitochondria, that's where the powerhouse of the cell. So this is just the structure of it. Each one of these we'll go in great detail about the 5th, 6 weeks. We do 6 weeks of cardiac physiology and EKG. Okay. Oops. And then just another one, just another look at the cell, how this disc, these Z lines and these discs contract, muscle contraction. It's really, it's not the same as skeletal muscle, but it's really close. There's a few things that differ from it, but a lot of it's like skeletal muscle. Has a lot of the different pieces that skeletal muscle has. And then again, the electrophysiology, one thing that's very unique about the heart is it has its own electrical system built into it. It doesn't require an outside stimulus. It doesn't require an outside source in order to create the action potentials or the electricity that flows through it. Because electricity is what makes muscles contract, right? Now this is not like a battery electricity. It's more of a positives and negatives with ions that's going to make it contract. And we'll look at that in great detail. Circle this word, syncism. What a weird word. You may have already heard that through the con videos. I don't know. Did he speak of this? Syncism? That's the ability that the whole, it makes it look like the whole heart is one cell. So when the heart contracts, it contracts together. The atrium contract together and the ventricles contract together. They don't contract at the same time because there's a layer there of non-conducting cells that separate it, so they won't contract together. But I think I'm pronouncing it right. Syncism, the heart, it looks like one big cytoplasm, one big cell, so it conducts all together. Because the heart contracts all together, correct? We've learned into a couple different terms, polarization and depolarization. Also, the term that we'll look at with depolarization is firing. It's just a sort of a slang term. They're used interchangeable. Sometimes I'll say the SA node depolarized. Sometimes I'll say it fired. That means the same thing. Even to break it down to really simple is it discharges. Right? It sends its action potential or its electricity. This is just a phase. Each cardiac cell has this phase, and what makes the cardiac cell contract is this sodium-potassium pump. This thing called a sodium-potassium pump. It uses sodium, uses potassium, and it uses calcium in order for that cell to contract. Again, for a later day, I'm just sort of giving you a trailer like they do at the beginning of a movie. Aren't you glad? Something to look forward to. Because I'm telling you, we will get knee deep in this stuff here. You will understand this quite well, or you won't do well in your exam. One or the other. You may not understand it, but if you understand it, then you'll do well in your exam. So we use, for this cell to contract, we use this thing called the sodium-potassium pump. So here on this graph, it starts at negative 90 volts, which at phase 4, sort of a resting phase. This is the resting phase of the heart. It'll get easier because you start looking at things in different phases. You have to really, really slow it down so we can see in our minds on different phases. When it happens, boom, like that quick. It's hard, like when something happens really fast, it's hard to see it when it slows down. So we had the phase 4, so this resting phase at negative 90 volts. When it comes time, I guess that's the best way to do it. When it's time, you're going to have this rapid flux of sodium and then a rapid flux of potassium, hence sodium-potassium pump. Phase 2, right here, is only in cardiac muscle. It's the influx of calcium, which extends the contraction out a little bit. We want to extend the contraction of that cardiac cell, that cardiac muscle out, so we'll get a good contraction. You've heard of fast twitch and slow twitch muscles. Fast twitch muscles are the ones that we used to sprint with. Slow twitch muscles are the ones we used to walk with. Anyhow, they polarize and depolarize very quickly. Well, that's not very good for the heart to do, because we want it to squeeze, right? We want it to squeeze and contract over a longer period of time, even though that period of time is quick. You know, we're talking second, less than a second, okay? But that's a longer period of time. Time is relative, right? You know, long, short, what's a long time? Right? I've been to a bakery that is older than the United States. So that's pretty old. Not compared to other things, right? I mean, in history. So we have this calcium. So you have this influx of calcium, and then the phase 3, the release of the calcium, the reabsorption of the calcium, and then back to phase 4. And this is what takes place every time that cardiac cell, a normal cardiac cell, conducts. After this, it contracts. Okay, so we have the sodium-potassium pump divided out into these different stages that, again, for another day. Because what we have is, we have a resting potential, like at that negative 90 volts, right? We have an action potential, that sudden influx of sodium, and then we have a repolarization phase where it's back down to negative 90 and it's repolarizing, it's recharging. So essentially it charges, discharges, charges, discharges. Does that make sense to everybody? Everybody good with that? And it does have nerves. It has sympathetic nerves and parasympathetic nerves. We're not really, these are autonomic nerves. We don't control this. We'll talk briefly about, we don't get into this in, probably next class, sympathetic and parasympathetic nervous system. But just so I don't leave you hanging until then, the sympathetic nervous system is the fight or flight. So when you get scared or something, your heart rate races up. Someone pulls out in front of you, you have to slam on your brakes, your heart rate goes way up. That's the sympathetic nervous system taking over, okay? Now, your heart can't stay at that heart rate, that increased rate, because it's outside of what? It's not homeostasis, right? So we have a parasympathetic nervous system that counteracts it, that slows the heart rate down. And it does it through chemical mediators that we'll learn about in a few classes. But that's sympathetic, parasympathetic. For right now, when you see sympathetic, it's going to be, you're going to say, okay, that's going to, a sympathetic response, that's going to increase the heart rate. Parasympathetic is going to decrease the heart rate. And we'll talk about these here. Let me get my cheat notes right quick. And we'll go ahead and define those words since they're up there on the board. These words here also correspond with medications. Okay, so we have chrono. Chrono would mean what? Time? Right? Chrono. So chronotropic, so if you add IC on that, chronotropic would be an increase in rate. Alright? So a sympathetic response would cause a chronotropic reaction to the heart. Make sense? Inotropic is the force or the strength of contraction. The force or strength of contraction. So you have chronotropic, time, rate, inotropic, strength of contraction, and dromotropic delays the conduction. Okay? And it delays actually the conduction through the AV node. That doesn't make any sense right now, but it will. Okay? So chronotropic increases heart rate or increases SA node impulses. Write that down for a definition now. Heart rate, chronotropic increases heart rate or SA node impulses. Inotropic increases force or contraction. And then dromotropic causes a conduction. It deals with the conduction speed of the AV node. Everybody good? Everybody good with those? And then you can't really see it. It's sort of at the bottom. I need to fix this. Role of electrolytes. The role of electrolytes, like sodium, potassium, calcium, we just talked about, right? So that's what creates the sodium-potassium pump. Skeletal muscles also contract on a sodium-potassium pump. It just varies different than cardiac muscle. And there's a nice picture of the heart. It's a little fatty, huh? This yellow stuff, this is fat. This is jack up the video, but I'll turn off the light for a second so you can see it. See the fat on the heart? These are coronary arteries. They just cut this. That's not supposed to be there. These are coronary arteries that deliver blood flow to the heart. And fat. Why does it have fat on it? No. That's fat is not desired. It's cause, that's a lot of blue bell right there. But why? Why does it have fat? Why does your thighs and all your other muscles have fat on them? I just gave you the answer. Because they're muscles. Muscles have fat on them. All muscles have fat. So the heart has fat. Does the brain have fat? Because it's not a muscle, correct? We'll take a great look at this during cardiac emergencies. These coronary arteries and these different parts. This here is just the top side. See the aorta? The aorta is the main artery in the body. It's big. It's a big artery. And from the aorta, all the other arteries branch off the aorta, right? What's this stuff inside? I can't hear you. No, that's not fat. It's hard. I'll give you that hint. Yeah, like a plaque. Plaque buildup. This vessel is supposed to be flexible. It is flexible, right? It's very flexible. What does this plaque cause? Huh? That resistance, yeah. What? Yeah, it's going to decrease the radius. What else does it cause for the vessel? The terms arterial sclerosis, hardening, right? Hardening of that artery. This plaque buildup causes hardening of the artery. So you'll get that in the aorta, and you'll also get that in the coronary arteries as well. And that's when we talk about heart attacks and different things. Arterial sclerosis is a big problem there. Keep a note on how big that aorta is, and then this branch here off the aorta, this big huge coronary artery going down. Okay, questions? Everybody good? Everybody hanging in there? It's a lot of information, but it's a lot that it's what we're doing right now is we're beginning a puzzle. Okay? And you know, one of those, like those 500-piece puzzles, I just threw it out there on the desk and got them all right side up. That's the beginning of the puzzle, right? Getting them all right side up. What's the next thing about the puzzle that we need to do? Huh? The corners, right? Get a good foundation. Let's make these corners, right? Set that corner on there, and then what do we do?
You join those specific colors together.
Yeah. But what do we want to do? We got the corners. Now we build what? Yeah, the borders. Okay, that's what we're doing right now. Essentially, is we're building. We're starting to get our corners in there. We for sure flipped them over on the right side. Okay, and now we're starting to put our corners in place and sort of sort out the pieces and build our border. By the six weeks, we'll have our puzzle just almost put together. And when you put more pieces of the puzzle together, what happens with the puzzle? Huh? What you say?
Oh, like you can see the picture.
There you go. You start seeing the picture clearly. You start seeing the picture, right? And then it gets easier to put together once you start seeing the picture. This is the same way. Once you put all these pieces together and keep putting them together, then it gets clearer. Until then, sort of, you got all these pieces laid out there. It doesn't make too much sense, right? So we have to wait on some of it. Some of it won't be till a long time from now. But it's all right. So let's go over the quick anatomy. This is not really the anatomy. Keep in mind that the atrium are not on top of the heart. They're actually posterior. They set posterior to the ventricles. They just had to do it this way so we could see it in the picture. But we'll run through the anatomy of the heart right quick. And we'll start on the venous side. So it's delivering blood that's low in oxygen, unoxygenated blood, back to the heart to be pumped to the lungs to reoxygenate blood, correct? So the inferior superior vena cava brings blood flow back to the right atrium, and it sits in that right atrium, okay, until there's enough pressure put on that valve. Anybody want the tricuspid valve? Very good. And so all the valves open due to pressure. So that blood, this blood here, flows passively into that atrium, correct? both atrium, the right and left atrium. It flows passively in there. There's not a valve at the top. There's just a hole. Okay, so blood flows passively into the atrium until there's enough pressure. And once pressure is built up in the atrium, then that valve will open. And once that valve opens, then this blood will flow through passively initially. And we'll get back, this is just another piece to the puzzle. It will flow passively through there until you get what's called an atrial kick. You should have heard that in the Khan Academy videos, correct? Cardiac anatomy, atrial kick. The atrial kick is essentially the atrium's contracting. It contracts. So blood's going to flow passively into this ventricle until we have atrial kick. And then the rest, not all blood, because the atrium never empty and the ventricle is never empty, but you get this atrial kick and it's going to force some more blood back through into the right ventricle through the open tricuspid valve. Okay? From the right ventricle, pressure is going to build, and then this valve here, the pulmonary valve, we'll just call it pulmonary valve. Okay, pulmonary valve. So open, and then the ventricles are going to contract, and then blood flow will go in through the pulmonary artery. Now, see, this is where it's different. Pulmonary artery, we're used to the arteries carrying oxygenated blood. But this fits the definition because blood is being pushed away from the heart, correct? So we have this. So blood flow through the pulmonary arteries. From this, it's going to go through the lungs. It's going to go through diffusion and become reoxygenated. Am I good? Then it's going to come back to the heart, oxygenated, hence the red. Blue's deoxygenated, red oxygenated. So it's going to come back to the lungs through the pulmonary veins, passively flow into the right atrium, then go through what valve? Mitral or bicuspid valve, whichever one you want to call it, and then into the left ventricle. We'll note when we see the heart, that the left ventricle is quite a bit thicker than the right because it does about 75% of the work. Does the greater workflow. Okay, so now the left ventricle is going to contract, and it's going to fill. Once pressure builds up in the left ventricle, it's going to force the aortic valve open and then push blood through the aorta into the rest of the body. Okay? It's going to reach the target tissue. Diffusion is going to take place because now we have our little toe that needs oxygen. So it's going to get down to the little toe. Diffusion is going to take place, and now the venous system is going to bring blood back to the vena cavas eventually, and we'll start the whole program over again. This happens all the time, right? With every beat of the heart. You are definitely responsible for blood flow through the heart, okay? That's another thing. I just keep adding things, don't I? So blood flow through the heart. Start really working on knowing the blood flow to the heart. I'll give you guys a good week or so before you actually see that on a quiz. If you see it like Friday, tell me. But hey, you promised a week, right? Okay. So, do you understand where this number is coming into play? Now, you guys are taking med-term and all that. You're ahead, right? You should probably already know this. Blood flow through the heart. So, you're ahead. And that's good. Now just get it where it's nice and concrete, nice and fresh. And there's this crazy picture of it and sort of how it goes. Eventually, you will understand the majority of what all this is right here. See this? I think this is cool. This time, you know, we talked about time, and it takes a longer period of time. It doesn't take very long. This is 0.0 seconds, right? So it's going through. The normal heart rate of an adult is 60 to 100 times per minute. And so, you know, 70 to 80 is the norm. But, so it happens quite quick. And then you have these different pressures in here that we will eventually talk about, because in the body, everything is about pressures. Each ventricle has a different pressure to it. The atrium has a pressure to it. That aorta has a pressure to it. What is that pressure of the aorta? You guys know that. The pressure in the aorta essentially is what? What pressure? Blood pressure. Right? I mean, we take a peripheral blood pressure, but that's pretty much what we're looking at. And then, of course, know the function of each part. It pumps, the atrium just receives blood from the inferior superior vena cava. Right ventricle pumps it to the lungs. Left atrium receives it back from the lungs, and the left ventricle pumps it out to the body. So just function, a little function of each chamber. Remember, 4 valves, 4 chambers. And then the valves, the heart valves, they prevent backflow. So when they shut, they're not 100% sealed, but they do create, or they keep backflow from taking place in that from the different chambers. That's why when someone with mitral stenosis, you know, they have a bad mitral valve, they leak blood back. They get backflow out of the ventricle back up into the atrium. And they have to go in there and replace that valve. They usually put a pig valve in there a lot of times. You know what causes the mitral valve to go bad? One thing? Energy drinks. Excessive caffeine is bad on the mitral valve. That's why these guys, they drink 2 or 3 energy drinks a day. They're killing their mitral valve. Okay, so we've watched that, right? Cardiac anatomy, that looked familiar?
The heart has its own intrinsic regulating system, known as the conduction system. This system generates and distributes electrical impulses over the heart to stimulate the cardiac muscle fibers and cells to contract. The conduction system begins at the sinoatrial node, or SA node, located in the superior wall of the right atrium. The SA node sets the pace for the system, thyroid hormone, and epinephrine. When the impulse is initiated, it spreads through both atria, causing the atria to contract. The impulse then spreads to the atrioventricular node, or AV node. The AV node, located at the juncture of the right atria and ventricle, then relays the impulse to the specialized muscle cells or fibers called the atrioventricular bundle, or bundle of His. The atrioventricular bundle distributes the charge over the medial surface of the ventricles to the right and left bundle branches to the Purkinje fibers. The stimulation of the Purkinje fibers causes the ventricles to contract. The cycle operates as follows. The impulse begins in the SA node, causing the atria to contract. The impulse is relayed to the AV node, atrioventricular bundle, bundle branches, and Purkinje's fibers, causing the ventricles to contract. The heart rests and the cycle begins again, usually 72 to 80 times per minute. This activity can be traced on an EKG. P wave equals T wave equals the heart at rest.